So as you can see, this is tutorial number 7, and in this tutorial we will basically what is called design the combinational circuits. So we have already seen how to simplify the combinational circuit if it has been already expressed in form of min term or in the form of table or in some other mathematical max term or some other mathematical form. So, but in real life, when you have to come up with a combinational circuit, the first step is to find out the mathematical expression of that combinational circuit. That means find out function. And finding out this function requires that you first find out the table, the list of all possible inputs and the outputs that you want for that specific circuit. So today what we are going to do, we are going to design. That means we will be given the problem statement, and from that statement we will have to find out the table, and then from the table we have to find out the mathematical function. And all these steps, they are called designing a combinational circuit. So I will first write what are the key steps involved in designing a Boolean function. So first step is you will be always given description of the situation or the problem in words. So from the problem statement, you have to first find out the table for the given circuit. Say function table. Then the second step is, once you know the table, we minimize the function that we have written, or whatever may be the number of outputs, using Kmap. So it is this second step that we went through in the last tutorial. And once you have minimized the function using the Kmap, its implementation using gates. So this third step is easier. Second step is little bit more difficult. First step is the most difficult part of designing any combinational circuit. So in today's class, actually we will be going through all the three steps, but we will see that for some of the cases, this first step could be very difficult. And if you recall the sixth or the fourth problem related with the door opening of an elevator given in the last tutorial, so that was the problem related with this first step, where we had to encounter the first step also. So now let us see what are the problems that we will have to solve. But in the beginning, some of the problems we will solve in a more common sense way. So here we have various problems for this tutorial. So first problem you can see is design a 4-bit combinational circuit, 2's complementer. That means there is a 4-bit combinational circuit which will give the output as the 2's complement of the 4-bit input. So output generates 2's complement of the input binary number. And then there is a restriction. We have to show that the circuit can be constructed with XOR gates. Right. So just try to see if you can design this circuit. So as I pointed out, this is the problem statement. From this statement, you have to arrive at the function table. That there will be a big table, and left side columns will contain all the possible inputs. Right side column or columns will contain the desired output. And once you're able to fill that table, then second step, which is using Carnot map, is easier.
Hello, sir.
Yes.
Sir, I have made the equations in the form of XOR gate.
Okay.
I have considered the output bits to be W, X, Y, Z,
Okay.
and W is equals to A XOR bracket में B plus C plus D.
Okay. And then.
And then my X is like B XOR of simply C plus D.
And then the remaining.
And Z is equals to D. It's like simple. Z is equals to D. There's nothing, you know.
Okay. So uh, here you can see that it says that with XOR gates. So you have used XOR gate, but then your implementation also requires OR gate. So try to implement using only XOR gates. Your answer is correct, but not fully as per the question demands.
So I have been able to find the equations, but I have yet to implement it in form of XOR gate.
Okay, fine. So here,
So
okay, let me solve it or try to show how to do this. So as I mentioned, there are two steps, three steps involved. The first step uh, is to convert problem statement into uh, the table. So here also, the first step is going to be converting this into table. So we have to do this thing for 4-bit number, right? So my system is going to be like this. So there will be 4 inputs and there will be 4 outputs. So let us call them as A, B, C, D, where D is the least significant. Similarly, here W, X, Y, Z. So we have to find out what is this circuit. And then it says that it should be using XOR only, right? So as I mentioned, the first step is to find the table, and that is the most difficult part. So here inputs are A, B, C, D, outputs are W, X, Y, Z. So since there are 4 inputs, so there will be total of 16 inputs possible, 0, 1, 2, so on so forth, going up to 15. So all these inputs, they will always be common for every problem, so on so forth. So for each of these inputs, we have to find out the 2's complement, right? And we know that 2's complement is simply complement of each of the bits and one added to it. So if you do the 2's complement of this, what you will get is all A, B, C, D will become 1, and when you add 1, they all will become 0. There will be fifth bit equal to 1 that we have to discard. So 2's complement here is going to be similarly this thing. Similarly here, we will have 1, 1, 1, and this 0 when added with 1 will become 1, right? So in this fashion, we will have to fill the table. So this is going to be 1, 1, 1, 0. This will become 1, 1, 0, 1, so on, so forth. So now what it says is that each of your output variables, W, X, Y, Z, they all are going to be function of 4 variables. W is going to be function of A, B, C, D, so on, so forth. Similarly, Z will also be A, B, C, D, right? And for each of the functions, we know the table. So table is known to us here. So this is the for function W, and then we can go for the second step, that is a K-map minimization of say W. So we will start with the simplest one, which is for the case of Z, for variable Z. This is the LSB. So this is going to be possibly simplest one. So here we have AB, here we have CD, and then you look at the table, and if you try to fill, what you will get is 1, 1, 1, 1, 1, 1, 1, like this. So here we will make the group of all the 8 cells, and
Hello,
for,
sir.
yes,
Why can't we just see from the table it is equals to Z exactly? We like there is no
yes,
need for
yes, you are
Kim.
right. For this case, it is very trivial. You can make this observation, but I am illustrating the general step that you will have to follow in all the cases. So here Z will be D,
Okay, sir.
right? So we are tracing those 3 key steps for this specific case, and some of the special cases might be trivial, as is the case with Z. Similarly, if you try to find out Y, then in that case, this will turn out to be C bar D and CD bar after filling the Carnot map and doing the minimization. And this you can straightway write C XOR D. So up till this, things are simpler. So this is the second variable. Now with the third one, situation is going to be slightly difficult. So for the third one, if you try to fill the table, which is for variable X, what we will get here is this table. So here we will have 1, 1, 1, 1, 1, and then 1, 1, 1. So this is A, B, C, D. So here things are difficult, as I pointed out. So this is one group, and second group is like this, and the third group is this one. So there are going to be 3 values, 3 terms. X is going to be equal to B bar D plus B bar C, and for the last one, B C D bar. So here, one of you pointed out that this can be simplified to B bar C plus D plus B C bar D bar, and this finally gets reduced to C plus D. So, but the question says that X, in fact, all the output should be implemented using XOR gate. But up till now, we have what we have found is in terms of OR gate also. So we have to get rid of this OR and get the XOR. So this step is can be simplified if we note that in adder, when you do C plus D, this basically amounts to doing CD bar or C bar D. That means doing C XOR D. So this will give you the sum part. Carry will be, of course, C into D. Carry is going to be C into D. But here you can look at that we are doing C plus D. That means we are interested in the sum part here. So that is why we can interchange this adder by XOR gate. So the X will become B XOR C XOR D. Right. Now, when we go for the fourth variable, where we will have all the four one, so that means W. So here table will be like this. So here we will have 1 1 1 1 1 1 1 and 1 here. Right, so this is going to be table for W. And now we can make group like this, 4 here and 1 here, another 4 here, and then finally 1 4 here. So as was pointed out one of you, this W will turn out to be A plus A XOR B plus C plus D. But just now, as I pointed out, this adder, they are basically XOR, so this can be written as A XOR B XOR C XOR D. Yeah. Right. So using the adder and some OR and XOR relation, we were able to convert OR into XOR. So now let us look at the second problem. So second part of this problem says that can you predict what the output functions are for 5-bit 2's complementer. So that circuit can be called as 2's complementer. And if we want to design 5-bit 2's complementer, then you can say that fifth bit is simply going to be XOR of all the 5 input bits. So extension is very straightforward. So now we are going to take up this question number 2. And here we will not follow all those steps. Here you will have to think in a different way. This is not exactly in that pattern, but remaining questions, they are of that pattern. So we have to use 4 half adders. Keep in mind, this is the restriction. We have only 4 half adders available to us. Hello. So we have 4 half adders available to us, and we have to design 2 circuits. In part A, we have to design a 4-bit combinational circuit incrementer. That means input will be 4-bit number and the output will be that 4-bit plus 1. Right? So you have to find out what will be that circuit using only 4 half adders. So just try to think that how you will implement.
Hello, sir.
Yes.
I have done that 4 adder part.
Okay, so describe how the 4
Actually,
adders.
I have considered input as A, B, C, D, and then where D is like least significant.
Okay.
And there are four adders connected in a series where like we start from like from bottom one, where is input as D and 1,
Hmm.
D and 1, and they get added, and we get output as sum and
Hmm.
carry.
Hmm.
We kept the sum, and the carry will goes on to the next circuit.
Yes.
Yeah, and this will goes on like in next circuit there is input as carry from previous circuit and C, and they get add up, and similarly this carry goes on.
Yes. You are right. So, so part A is a bit simpler. So what we have to do is actually implement one incrementer. So we have to basically do x plus 1. This is what we have to implement. So, and x is 4 bit. So let us say x4, 3x3, x2, x1, x0. These are the 4 bits. And to this we have to add 1. So that means 0, 0, 0, 1. This is what we have to do. So the first bit will add x naught and 1, and we know that whatever carry comes, that carry will move to left side. And we know that in one half adder, we have two inputs, and one is sum, other is carry. So here we have uh, say x and y. So this x is going to be s is going to be x or y, and this is going to be x naught y, x into y. So here we see that carry will be in general generated at all the stages, and this problem is simpler. We have to simply keep on taking care of the carry from the previous stage to any given stage and find out the sum. So in this case, let us first add the initial two bits. So we take half adder, we give x naught here, we give 1 here. This will generate sum as 0, and then it will generate carry C0. But now this carry generated here at the first stage will propagate to the second stage, which actually had to add 3 digits. So what will be those 3 digits? X0, X1, and C0 that has come from the previous stage. But since the one of the bits is 0, so that can be overlooked, and we can add simply the X1 and the carry. So we take the advantage of this. Otherwise, it would have required full adder. So we give X1 here, and we bring the carry from the previous stage. So this is half adder. Similarly, the carry generated here will go to the next stage, which will add with third bit, and the last stage will add the third bit with the carry. So here the desired quantities will be given by S0, S1, S2, S3. So this will be the output. So this problem is simpler because the other bits were 0. That is why we could using half adder. But now let us look at the part B. So part B says design a 4-bit combinational circuit decrementer. So a circuit that subtracts 1 from a 4-bit binary number. So earlier we were adding 1, now we want to do subtraction. So, but the restriction remains same, that you will have to use the 4 bits, 4 half adders only. So this time what you have to do is implement x minus 1 with 4 half added. This is the restriction. So try to solve this problem. No additional circuitry should be used. See, when we want to do subtraction in binary, that means when we want to do x minus y, we try to convert it into addition. That means x plus 2's complement of y. And here y is equal to 1. That means it is 0, 0, 0, 1. So if you try to solve this problem x minus y using only 4 half adder, using this general technique which is used in binary, then you will not be able to solve it, strangely enough. So what you will have to do, you have to find out this x minus y in the usual way, I mean the normal way in which we do the subtraction. So trick is that you simply subtract 1 from x. So using the normal subtraction, what you will do is, so x minus 1 will be, say, x3, x2, x1, x0 minus this. And you do this thing in usual way, like you do the subtraction of two decimal numbers. So if you do in this way, you will succeed. So now just try to see whether you are able to do it or not.
So can you please repeat just once
So,
what you just said? Can you just repeat?
okay, so what I
Today.
told was that when we try to do x minus 1 in binary, we try to convert the y, the number which we want to subtract, to its 2's complement form and then simply add to the x. This is how we
Okay.
do in binary, and this we do so that we can use the same adder for both addition and subtraction, and thus they minimize the circuit size. And
Okay.
in this case, y is equal to 1.
Okay,
So
sir.
this is how you will try to attempt solving this problem. But if you do, you will not succeed in this way, because restriction is you will have to use 4 half adder, and this technique will require inevitably full adders also for
Okay.
the second, third, and fourth bits. So what I said, that you forget this new technique of 2's complement for the binary, you go back to your usual subtraction technique that we have been using for the decimal numbers. This technique that you have this number and you are subtracting 001 from x3, x2, x1, and do this thing in regular way, and then try to implement using half adder, and you will succeed.
Okay, sir. Got it.
Okay, one more hint, that you try to first imagine if you have only one bit subtraction to do, because here the four half adder restriction arises because the number has 4 bits. That means if we are to subtract or solve this problem for 2 bits, then of course we will have to use only 2 half adders. So let us consider the simplest case. That means we have only 1 bit subtractor. So we have,
Okay, sir. I got something, I think.
ठीक है, if you got, then that is fine. So 1 bit subtractor means we will have to do, or rather decrementer. So let me say this is decrementer. So we have to do x naught minus 1. So now x can take only two values. So this will lead to two possible cases. 1 minus 1, which is 0, that is the trivial, and more difficult cases, so 0 minus 1. So this cannot be done on its own. This is possible. So this the second one requires borrow from the previous stage. Now suppose we have this one case and we want to use half adder. So can we do this? So answer is yes. You can see that this sum is simply the XOR of x naught and 1, right? Or you can also say this is x naught plus 1. So actually it will be better to see in this way. So we know that half adder basically does this thing. So we can take simply one half adder, give it 1, and 1, this one is what we want to do the subtraction. This is in place of x naught and this is in place of, say, y naught. So the result that will come here, s naught, is going to be 0, and this is fine with us. We are not interested in carry. Carry exists, but it is of no use to us in this way. So using 1 bit and using the simpler case when x naught is 1 is fine. Here, this we are able to do. Now what about this? So when x naught is 0, we of course require one borrow. So this can be handled only when you have this scenario, that is x1 is 1 and x0 is 0, then only you can do the subtraction in the usual way. So what will happen here? So there will be one borrow from the previous stage. So when 1 comes here, this will become 1 0, that means 2. 2 minus 1 is 1, and this becomes 0. x1 becomes 0, so this is 0 minus 0. So this is going to be the result, right? So now when we want to use two half adders, so now we have 2 bits, so there will be two half adders involved now. Half adder 1, half adder 2. So this is x naught, this one is 1. This sum, now you can see there is 1. So whenever x naught is 0, this added with 1 will give you 1 here. So this will work fine even when x is 0. For x is equal to 1, we have already seen this is working fine. So now we have to bother about the borrow thing that we are taking from x1. So now you can see that what is the bit that we are getting at the second position after the subtraction, it is 0. So here you can see that x1 is 1. x1 is 1. Now if you add this x1 1 with the s0 sum that you are getting, so that will result in 0. So what you can do, you can add this s0 with x1. So that will result in 0 here. For the S1, output is going to be 1. Sorry, it is going to be 0. So you can say that we are getting what we wanted. 0 here, 1 here, and this is what we are wanted, 0, 1. Right? So here you can see that the sort of the sum is propagating to the next stage and getting added with the next bit. So now if someone says that you design a 2-bit decrementer using half adder, then this is the circuit that you will design, right? But now what we have to do, we have to design a 4-bit. So we have to evolve from this 2-bit to 3-bit and then to 4-bit. So In the 3-bit configuration, the more favorable scenario will be like this: 1 1 0 and subtract 0 0 1. So here we see that the first two stage is similar to this one, and because these two stages, they are able to lead to the subtraction 0 1. So this 1 and 0, this will remain as it is, and what you will get is 1 here, 0 here, 1 here. And now you see that what has been generated here for the second bit, the sum S1 is 0. So this can be now added with the uh, third bit, that is X2, and you will get 1. So for this case, you can design uh, decrementer using 3 half adders. This is 1, this is X0, this becomes the S0, this is X1, and S1 then goes to next stage, and this is X2 here. So this is going to be sum 2. So these S0, S1 and S2, they are going to be the difference of, or the decremented value. So here we have a very favorable scenario that this third bit didn't get affected. No borrow was transferred from third bit, only the second bit borrowed to the first one. But more difficult scenario could be like this, having 1 0 0, and then you are subtracting 0 0 1. So in this case, you can see that first you will have to take borrow from here, 2, this will become 2, and then this 2 will give a 2 to here, and this will become ultimately 1. So the result is going to be, this is going to be 1, this is 1 0. Now here you can see that the circuit that we just now designed is going to work fine for this case also, because in this case you can see that result is going to be 1 1, right? Now this 1 is going to get added with X2, which is 1. So we are adding 1 and 1, so of course this is going to be 0, and this 0 is what we are getting here. So we see that this circuit that we have arrived here works fine for 3-bit kind of scenario. Worst case scenario, this is the worst case. Worst case in a sense that the borrow is coming from the most significant bit ultimately to the least significant bit. So starting from here, borrow is propagating all the way down to the rightmost position, least significant bit, right? So now you can possibly guess that if we have the worst case scenario for 4-bit type of thing, that means 1 0 0 0, and we have to decrement this one by 1, then you can say that borrow will propagate first from here to here. This will be 2, then 2 will come here, then this 2 will come here, 2, this will become 2, this will be 1, this will be 1, and this will become 0. So the result is going to be 1 1 1 0, and this is what we have to get from the circuit. So we have already covered scenario up to 3 bits. So for the 4th bit, here you can see that if you take this one, which is going to be S2, which we are anyway getting, and if you add this to X3, so that means if you add X3 and S2, which is going to be 1 plus 1, result is of course going to be this 0, X3 plus S2. That means you need simply another half adder to perform this addition, X3 plus S2. So the complete circuit will be like this. So here sum from one stage will propagate to next stage. So this is X0, this is 1, it generates S0, this S0 goes to next stage, which has input X1, then the sum S1 goes to the third half adder, which has input X2, then sum 2 goes to the last stage, which has input x3, and each of these are half adders, and these are the my bits of interest. So what you will get here is one decrement. And in all these cases, these carries, they will not be of any use. This C3, C2, C1, C0, they are of not interest in interest. Right, so key point here was don't go for the 2's complement way of subtraction, go for the usual way of subtraction, and then you will succeed. Okay, so now there are other questions where you will have to follow those 3 steps that I pointed out. For example, here in question 3, you have to design a combinational circuit that converts 4-bit gray code to 4-bit binary number, and then implement using XOR gate and using NAND gates. So that part you can try out. So here I will quickly just explain what are the gray codes, how they are written. So here also you will have to fill a table where on the left side you will have a gray code, and on the right side you will have the normal binary numbers. So this gray codes, they are also called reflection code. So there could be 1-bit, 2-bit, 3-bit gray codes. So how do we create these gray codes? And that we use with the help of its naming called reflection code. So when you have 1-bit gray code, so there are only 2 gray codes possible, 0 and 1. Obviously, these are the only 2 possible gray codes. But now suppose you want to have 2-bit gray code, then there will be total of 4 possible gray codes, and what will be their ordering? And keep in mind that these orderings, they correspond to the ordering for the decimal number. So as I pointed out, they are also called reflection codes. So how do we generate gray codes? For that, what we do, we take a 1-bit gray code and assume there is a mirror here. We put a mirror below this gray code that we have already written, 0, 1. What mirror will do? It will create image. It will create image like this, 1, 0. So 1 is copied here, 0 is copied here. So these are the 4 least significant bit for 2-bit gray code. This should be G1. Now what we do for the second bit? For the second bit, above the mirror we put 0, below the mirror we put 1. So this is the 2-bit gray code. Now when we want 3-bit, we put another mirror here, and now simply copy the older ones. That means 1, 0, 1, 1, 0, 1, and 0, 0. Now for the second or third bit, we put 0 above mirror, 0, 0, 0, 0, and 1 below mirror. So this is how this table can be filled. So once you fill this table, you will have to, on the right side, you will have to write your W, X, Y, Z binary numbers corresponding. So binary number for 0, you write binary number, for 1, you write binary number, so on and so forth. So you will have 3 Boolean functions, W, X, Y, Z, each depending upon all these 4 gray code variables. And then with the help of Carnomat, you can find out what will be the Boolean function for W, X, Y, and Z.